Hello everyone, so in this video I'm going to be showing how we complete the Lab 3 Ohm's Law and voltage divider circuits by going through the exercises. I'll be demonstrating on a virtual breadboard, but I'll be drawing everything out. So the first part of the exercise requires us to measure 3 resistors, each with 3 different values. If you don't recall how to do this to determine the resistor color code, I would advise go to Lab 1. But simply, if we wanted to measure resistors, we just simply have to put our probes across the ends of the resistor and having our multimeter on the ohm measuring mode. All of those steps are explained in Lab 1. So now, to move to the next step, once we have all those resistors measured, we're going to build this circuit, and for each resistor, we'll be applying different voltage values and recording the voltages across the resistor. Current through the resistor. So just going to the circuit board now to show you. So here I already have the circuit displayed from our lab. I'm just going to go ahead and take a picture of that. So we have our circuit here applied on the circuit board, the breadboard. And let's assume for this presentation that the left column represents the voltage source that we've connected our jumper wire to the breadboard breakout, and then the right column represents our ground, which we connected our jumper wire to the ground pin on the breadboard breakout. So now that we have all that established, the proper connections to set up our side rails, now we can go ahead and work with the circuit. Now, as you can see, I have the direct implementation of the circuit from the schematic to the breadboard. I have the positive connection connecting to the one end of the resistor and the ground end connected to the resistor. So therefore, there's a completion of the circuit. As we know, each row is electrically connected. I could put my resistor on any end of this breadboard. I could put it on any set of holes along the row, and it will still be electrically connected. So in this way that I have right now, you can see that the jumper wire is connected to the third hole in the row, but it is still connected to this end of the resistor. And same thing with this end of the resistor. This end of the resistor, even though it's not in physical contact, because they are in the same row, they are electrically connected. So this circuit is complete and electrically connected, and with the voltage applied, there is current flowing through this circuit. So now, in order to measure the current going through the circuit, we have to break the connection. And breaking the connection means that we have to stop the flow of charge. So the best way to do is just connect the part that is creating the completion of the circuit. So the best and most practical solution would be to move the black jumper wire that's connected to ground, that's connected to this end of the resistor. Therefore, at this moment, there is no completed circuit, and there are no charges flowing. So now we have to move on to the next step where we want to measure current going through the resistor. So I'm just going to go ahead and take a picture of my circuit. So now we have broken the connection of our circuit, and now we need to complete the circuit using our ammeter. So the best way to do this is to have our ammeter suppose this is our ammeter, and we have it set on DC amps, DC milliamps. and I need to connect my probes to this circuit. Now we need to be aware of the direction of current flow. We do know that current flows from positive to negative. So the positive voltage source is going to allow charges to flow in this direction. It's going to flow through the resistor. So we must complete that circuit. So we're going to connect our red probe from this point to our ammeter. Then the black probe to this point, the ground jumper wire on the circuit. And so therefore charges will continue to flow through the red probe, through the meter. The meter will give a reading and detect the amount of flow, and charges will continue to flow through the end. So we can connect our probe to the metallic part of this resistor end, while with the black probe we have to connect it with the end of the jumper wire in order to complete the circuit. Now once we obtained the values and recorded them, we can insert them on the tables. Now for table 1.1-2, you see I've already made these, I've entered the data, but I'd like to demonstrate how I obtained these solutions. I'd like to show you how I can obtain these solutions, these values, theoretically. So we can verify our results by doing Ohm's law, doing the actual math for Ohm's law. So we know that Ohm's law says V is equal to IR, or conversely, I is equal to V divided by R. Now, what we have in our circuit is we have a voltage source with one resistor connected to ground, and the voltage source varies. But the resistor, in this case, I'm going to use R1, which is equal to 1k ohm. Now, solving for current, I can just go ahead and write Ohm's law. So I is equal to V divided by R. And I know that voltage is equal to, let's do the 2 volt case. 2 volts divided by 1 kilo ohm. Now we've written, as you have learned in the previous labs, that 1 kilo ohm represents 1,000 ohms. Or we can also write 1,000 ohms in engineering notation as 1 times 10 to the third. Now by doing the algebra here, we can see that if we broke this down, 2.0 volts divided by 1,000 ohms, or 2 volts divided by 1 times 10 to the third, we can see that this 2.0, we can see that we need to apply more algebra in order to get the correct metric prefix. So I can also represent 2.0 as 2.0 times 10 to the 0 divided by 1 times 10 to the third. Now applying one of the exponential laws, such as a to the m divided by a to the n is a to the m minus n, we can apply that same rule in this case. So in this case, a represents 10 to the exponent, either m or n. So we have the constants divided, multiplied by 10 to the 0 minus 3. So 10 to the 0 minus 3 is equal to 10 to the negative third. Using the metric prefix, it's going to be 2 milliamperes. Obviously, once you get enough practice, you don't have to do 10 to the 0. It's just for you to visualize how the exponents work when dividing a a value as small as 2 by 1000. Now, repeating those steps, we should be able to get these results. These are the theoretical results. These are not experimental results. So once we gathered all our data, we can go ahead and enter it in the curve. So the way we enter data in the curve is we go ahead and right-click on the graph, go to Edit Data, and select Edit Data in Excel. We'll open a file. If you don't have the file, just go ahead and let me know. I'll email it to you. So simply we write in the I column, you can see here in column B, it's for the results that we obtained for I1 at voltage 1 volt, I1 at voltage 2 volts, I1 at voltage 3 volts, and so on. And same thing, so this would be for the 1K ohm resistor, this would be for the 1.5 and the 2.2, I believe. Those are the resistor values, if I'm not wrong, but you get the point. So you want to measure your values in milliamps. And once you enter those values, you don't have to save the file. You can just go ahead and close it, and it will plot the data automatically for you to scale. Now moving forward, we have the voltage divider circuit. So in this part, all we have to do, the first part we have to do is calculate VB. So just go ahead and do that for a 1K ohm and a 1K ohm resistor circuit. So I'm just going to go ahead and draw that out. Now to calculate it, I'm going to have 3 volts applied to the circuit. This is my 1K ohm, 1K ohm, and this is V out. It's going to be measured with respect to ground. So the voltage divider equation says the voltage we are interested in is equal to the supply multiplied by the resistor of interest divided by the sum. So in this case, we have a 3-volt resistor divided by R2 is 1K ohm, and R1 is 1K ohm, and R2 is 1K ohm. So what happens is 3 volts multiplied by 1K ohm, and because the denominator is in the same metric prefix, basically 1000 plus 1000 is 2000, then the units do not change. So in this case, we should have 2K ohms in the denominator. Now you can see that we need to do the algebra here, but again, we have to apply the exponential laws. A to the m divided by a to the n, which results in a to the m minus n. So in this case, for 1K ohm divided by 2K ohm can also be represented as 1 times 10 to the third divided by 2 times 10 to the third, which that is 1 divided by 2 times 10 to the third minus a third. 3 minus 3 is 0, so we have 1/2 times 10 to the 0. 10 to the 0 is equivalent to just 1. So our result, VO, is equal to 3 volts divided by 1/2, which is half is 1.5 volts. As you can see, the voltage was divided in half because we have 2 resistors of the same value in series. Now we can do the same thing, and I'll show you how we connect it in the circuit. So here, all we have to do is add the same resistor. These are not the correct resistor values. They might not be. these are only for demonstration purposes. So you can see here, I have my two resistors in series. I have the power, the source connected to this end of the resistor, and the ground connected to this end of the resistor. Everything is electrically connected because the points that I need them connected are all on the same row. So I just do it with the actual circuit. Oops. So this represents my circuit. As you can see here on the red wire, all these points are connected. So that is basically, this row represents this entire section on the schematic. Although we know that there's some wiring on the resistor, so part of that we can say is this end of the. So the rows are obviously represent this connection point on the circuit diagram. Now this connection point represents this section on the circuit diagram, or we can just call it this point. And likewise, we can have this section of the circuit board is representing this entire connection point between the ground of the supply, the end of the resistor, and this point that's connecting both parts together. So the way I would measure the voltage across these points with respect to ground is I would put for VA, we have VA here and VB. So I need to just measure my source. So what I just have to do is put with my multimeter, in DC mode, DC volts, it could be millivolts. I just need my red probe connected to this point, and so V volts, and then my black probe connected to this point. This is my common, because the black probe just needs to be connected to ground so that we're measuring reference to ground. So that's how I get VA, and I should expect a result near 3 volts. Now VB, I just have to take my red probe and I could either connect it to this point on the circuit, or I can connect it to this point on the circuit, because um, either or, since they are electrically connected, I should get the same result. It doesn't matter which end I choose. I could even put a jumper wire if I wanted to and have it sticking out and measure the voltage on that point. But all these points are electrically connected. They have the same voltage at this point in the circuit. And the same thing with the black probe. I can just go ahead and connect it right here to the ground because we're measuring in reference to ground. And so VA should be around 3 volts approximately, and VB, we should expect a value around 1.5 volts. If you're not getting something around this, then you're either measuring incorrectly, It could be one of the, well, like it could either be multiple reasons. You don't have your circuit set up correctly. You are not measuring, so circuit um, is incorrect. Another reason is that you're not measuring incorrectly. You're not measuring correctly. Measuring incorrectly. A third reason is that you have the wrong resistors. A fourth reason is that you don't have the multimeter in the correct setting. Or terminals. And the last reason would be you don't have the voltage supply at the correct voltage. Now let's begin with exercise 2-2. In 2-2 it says design a voltage divider that divides a voltage by a factor of 3 at the output when driven by a 3-volt supply and only using two resistors R1 and R2. Measure and record all resistor voltage and current values in table 2-3. Be sure to show all your work. And I want to do a similar problem not using the same numbers. So let's go ahead and just draw a circuit, the voltage divider circuit. And you should have noticed that with two resistors of the same value, divides the voltage in half. So R1 and R2 are, in this case, they're unknown. But we do know that the output should divide the voltage by a factor. In this case, I'm going to say divides a voltage by a factor of 5. So divides voltage by a factor of 5. Okay, so here's our output terminal or output, and here's output, and we're measuring the output with respect to ground. So the first step is to write what we know. Oh, let's say the voltage is driven by a voltage source of 3 volts. So we have to find the resistors R1 and R2. So the first thing is to define values we know. So we know that Vs is equal to 3 volts. We know that R2 and R1 are unknown. And we can define the output voltage. It says in our problem statement that we want a output voltage voltage divider that divides the voltage by a factor of 5. Therefore, we can say the output voltage is a factor of 5, or it's either 5 times the voltage is equal to the supply, or we can say the output voltage is equal to 1/5 of the supply. So define. Now we can write down what we do know about voltage dividers. We know that the voltage divider is represented by this equation. So if we look at this equation, we have 3 unknowns. We don't know what voltage VO is, we don't know what R1 is, and we don't know what R2 is. However, in our definition, we do have VO written equal or equated to Vs by a factor, by 1/5. So therefore we can write VO in terms of Vs. So we can just go ahead and write the equation. again, one more time. Just go ahead and write equation here. So VO is equal to 1/5 VS. Oh, you know what? That would actually be a good thing to write down. 3 is unknown. Let's see. VO, R1, R2, and then identify relationships. 4 is identify relationships. That the relationship we identified was VO is equal to 1/5 VS. So now we use this information we gathered to complete this design. So we're going to rewrite equation 2. So equation 2 says that 1/5, we're writing VO now in terms of VS. 1/5 VS is equal to VS times R2 divided by R1 plus R2. Now, all we have to do is do the algebra and see what we get. So the first thing I can do is cancel or multiply both sides of this equation by the reciprocant of Vs, or divide both sides by basically the same thing. So I can divide both sides by Vs. And algebraically, these shall cancel. And so all we're left is with 1/5 is equal to R2 times R1 plus R2. And so now I just have to perform some algebra. So I can multiply 5 to both sides. So I get 1 is equal to 5 times R1 over R1, R2 plus R1 plus R2. And then now I can to simplify this even further, I can multiply both sides by R1 plus R2. And I should get R1 plus R2 is equal to 5 times R2. Now I just have to create another relationship I can see here. So R1 is equal to 4, 5R2 minus R2, because I subtracted R2 from this side to go on this side. So 5R2 minus R2 is equal to 4R2. Therefore, the relationship between the resistors is that R1 should be 4 times R2, or R2 is 1/4 of R1. Either way will work. So we said that R1 is equal to 4 times R2, or likewise R2 is equal to 1/4 R1. So if we select, let's do R1 is equal to 1k ohm. Therefore, 4k ohm. Therefore, R1 or R2, let's say if R1 is equal to 4R2, then R2 is equal to 1/4 times R1, which is 1/4 times 4k ohm. So 4 divided by 4 is 1k ohm. R2 is 1k ohm. Okay, so that's our resistor values. Let's go ahead and check our math. So VO is equal to 3 volts multiplied by 1k ohm. 1k ohm plus 4k ohm. So 3 volts is multiplied by 1k ohm and 5k ohm. So 3 volts times 1/5 is equal to 3/5 of a volt. So our answer checks out. Now the steps are similar to solve for lab for exercise 2-2. So the steps are similar. Although the resistor values are completely different, I'd suggest to do the same steps as as I followed. First, you define what you know. Then you write equations that apply to this problem. Then 3, you identify your unknowns. And 4, you identify relationships. And this will help you solve this design problem. That'll complete the video for today. Hope you learned something and got something out of it. If you have any questions, go ahead. Feel free to email me anytime.